So today's lesson is on Pascal's Principle, okay, and we're going to go over the hydraulic press. So we've talked about the difference between liquids and gases as fluids, and the one property that is going to be important for today's lesson is that liquids are not very compressible. That means their volume pretty much more or less stays constant even when you apply pressure onto it. So when we apply pressure to an enclosed liquid, every part of that liquid, that pressure gets transmitted through. This is called Pascal's Principle. Okay, and we actually used technically somewhat of a hydraulic press in class when we had the two syringes filled with water. When you pushed one end, that pressure that you exerted was transmitted to every single part, right? Which is why the other end immediately responded. Okay, and this is the device, the hydraulic press, that Pascal used this principle to help design. You might have a small piston and a large piston. I mean, you could have them the same size, but there's no advantage to having them the same size. So if you have a device in which you have a small piston, which then can transmit pressure through enclosed liquids, it's important that it's not gases because gases are compressible. And then we'll apply a large force on a large piston. So that has an advantage, right? You apply a small force on one, you get a large force on the other. But there's always got to be a price. And you did this in the lab. I had you analyze the distance that they each move at. Okay, so you always, if you get force, you pay with distance. So let's look at this example of a hydraulic press. So when you press a force on this piston, which has some sort of area, okay, that pressure gets transmitted throughout the fluid and exerts a pressure on this piston. Now, Pascal Principle says that those pressures are the same. The pressure you exerted on the small one is the same as the pressure that was exerted on the large one. But since pressure equals force over area, right, there's nothing that says the forces must be the same. So if the areas are different, the forces will be different. So if you have a smaller area over here, then you must also have a smaller force required so that these ratios are still equal. This will have a larger area with a larger force. So when you press down with, say, a force of 10 newtons, if this area is twice as big, it'll exert a force of 20 newtons on the piston. So let's try an example. Okay, here's the sheet we're working on. Lesson 21, Pascal's Principle. And we're going to do question number 1. So we have a force of 14 newtons applied to a piston of area 0.01 square meters, which is connected to another piston of area 0.25 square meters. What's the force of the larger piston? So here's what we have. Let's look at this diagram. So here's our smaller piston, which will have an area, say A1, equals 0.01 meters squared. And our other piston, which is connected to it, has A2, where A2 equals 0.25 meters squared. Okay, and then we apply a force here of F1, which is 14 newtons. And the question says, what will be the force that is then applied on the larger piston? So this is the equation we're going to use. Okay. It's the same as this equation. We can just rearrange this equation. Okay. If you simply sort of cross multiply these, your area will go up here, your force will come down here. And that would be equivalent to what is down here. But to make things simple, actually, let's just start with this. That is Pascal's principle. The forces must be the same. So let's say the pressure on the first piston must be equal to the pressure on the second piston. So pressure is force over area, so I'll do F1 over A1 must equal F2 over A2. Now we want to solve for F2 here, so let's rearrange for F2. It's up here, so if I multiply both sides by A2, I will get F2 equals F1 times A2 over A1. I'm running out of room, so I'm going to continue up here. So let's put in all of our known values. So F1 is 14 newtons. Our second area is 0.25 meters squared divided by our first area, which is 0.01. Alright, so when you put that on your calculator, this gives you pascals divided by meters squared, which is going to give you newtons, and we get 350 newtons. So let me just pause it there. So let's go over an application of this. So looking at car brakes. Now car brakes have simple machines, so they have levers, but they also have hydraulics. So we did experiments with hydraulics when I had you in class because they are kind of a simple machine, right? You change the force by changing the distance that force is applied for. So first we have the distance from the pedal to the pivot is 4 times the distance from the cylinder to the pivot. So the force at the pedal will be increased by a factor of 4. So that's the first step. Right? You increase the force by a factor of 4. If you remember, this is a second class lever. Next, you have your hydraulic system here. So the diameter of the brake cylinder will be 3 times that of the pedal cylinder. Which means, since we have a much larger area, and area is pi r squared, right? If we are tripling that diameter, then the area is increasing by a factor of 9 of 3 squared. Right? Now multiplying the mechanical advantages of 4 with the mechanical advantage of 9, we get a total mechanical advantage of 36. That means the force that you apply with your foot gets multiplied by 36. So if you apply 100 newtons of force on the pedal, 3,600 newtons of force will start squeezing on that wheel. So it's quite impressive. This was a fairly short lesson, but let's go over. I want to make sure everybody understands these things. So question number 2, if you know the answer, you can just type A, B, C, D, or E into the chat. Okay. So in a hydraulic system with 2 pistons, right, just like the one we experimented with in class, I don't have it on me, I already put it away. Piston A is half the diameter of piston B. Okay, so this is important. If it's half the diameter, then it's also half the radius. And the area of a circle is pi r squared. So I just want you to remember that. Okay, so piston A is half the diameter of piston B. So piston A is the smaller one. The pressure on piston A is blank the pressure on piston B. Is it 1/4 the pressure, 1/2 the pressure, twice the pressure, 4 times the pressure, or the same pressure? What do you think? Try typing A, B, C, D, or E into the chat. Okay, somebody's saying B. It's a good guess, right? But you're thinking of forces, not pressure. Okay, the forces can change when the area changes, but the reason the force is able to change when the area changes is because the pressure is always the same. Okay? And pressure is force over area, so if you change area, you can change force, because the pressure will always remain the same. That's Pascal's principle. The pressure is always the same as it gets transmitted to our hydraulic press. All right, question 2. The force on piston A is blank. That should say force on piston B. So the force on piston A is blank the force on piston B. What do you think? Quarter, half, 2 times, or 4 times? Let's do a little process of elimination first. The force on piston A, is it going to be smaller or larger? Okay, the force on piston B. Okay, remember piston A is our small one. Piston B is our large one. Okay, so larger area, larger force. Smaller area, smaller force. So the force on piston the force on piston A should be much smaller than the force on piston B. So it should be one of these two. Which one though? Now piston A has half the diameter. So you might guess that the force would also be half. But pressure is force over area, not force over diameter. And the area is pi r squared. So the diameter, or half the diameter, will need to be squared. So if it's half the diameter, it's also half the radius. And 1/2 squared, or 1/2 multiplied by 1/2, is a quarter. Let me just pause it there, see how everybody's doing. All right, so because we can actually have an increased force, we have a mechanical advantage. Now, ideal mechanical advantage. So remember, we're going to ignore things like friction. So we're not going to talk about actual mechanical advantage. So the ideal mechanical advantage, if the force is applied to piston A. So you have your small piston. If you apply a force to there, you get 4 times the force on the larger piston. So that's a mechanical advantage of 4. Right? You're just taking the ratios of your large force over your small force. So it's 4 over 1. Now the ideal mechanical advantage of the system, if you apply a force to piston B. So if you apply a force to the large one, you get a much smaller force coming out of the small one. So that's a mechanical advantage less than 1. And in this case, it's 1/4. Okay, for the same reason as question number 2, you get 1/4 the force that you applied to piston B coming out of piston A. All right.